Do you hear me? Yeah. So thank you, Martin. So can there be a better way? And now we're going to talk about an actual implementation which follows. Yeah, so this one. Which follows all these architecture we have discussed so far. And the basic system, the basic virtual machine we have chosen is called WebAssembly. Just to recap, WebAssembly is designed to be fast and efficient. It is designed to be a secure sandbox, which is very similar to EVM. EVM is designed to be a secure sandbox as well. It really aims to have a widespread toolchain compatibility. So what it means is LLVM, which you might heard about, is a compiler toolchain, and it has a lot of different targets, like regular CPU. But it also has a target for WebAssembly. And that means any language which is supported by LLVM, which includes all the major languages such as C, C++, etc., can be compiled to WebAssembly. We don't need to invent compilers again. And lastly, the fourth really big point of the design goals of WebAssembly is that it has to be extensible. So who's actually making WebAssembly? WebAssembly is made by the W3C working group, which counts over 600 participants, and all the major browser maker companies are participants of this group. So let's just stop for a second, with instruction sets. There's a way to group instruction sets, categorize them, is by the number of instructions they contain and how complex those instructions are. And this split is called CISC, or complex instruction set computing, versus RISC, reduced instruction set computing. We could consider EVM a CISC instruction set because it has all those special instructions to extract the state, such as address, origin, etc. In comparison to that, WebAssembly is designed to be a RISC instruction set. It tries to be very limited. It has integers and floating point operations, and it is defined as an annotated stack machine. I don't want to really go into detail here, but what that means is it has to be easily processed, it has to be easily transformable, and it has to be able to be implemented using a stack machine or JIT. The JIT part is really important because that will fulfill the goal of speed. Okay, this might look a bit technical. This is just an example how you can represent, how you can visualize WebAssembly instructions and modules. One interesting point to mention is WebAssembly isn't just an instruction set, it isn't just a bytecode. It also defines a container format. So that's pretty much like an executable on your computer. It doesn't only have instructions, it has metadata on how to process those instructions. Here you can see that we have separate parts of that container. And like the first part is an import statement. And that way we can refer to external methods. We can also export our own methods. We can define memory. We can define functions. And in this part is the actual bytecode you would imagine as bytecode. Just a recap of all what you have seen there is we have multiple types. We can have immediates, all the usual stuff. And the most important part is to have calls. Because we don't really want to have a complex instruction set. We don't want to have all these separate instructions part of the bytecode. We just want a simple way to call methods defined outside. But as expressions, the textual representation isn't the best way to transmit bytecode. It has to be more compact. So here's an example how the bytecode actually looks like. And I just put it there to show that it's not, it wouldn't be that big compared to EVM. And this bytecode itself is the version what you have seen before in as expressions. So it is designed to be fast at decoding. It is designed to be fast at decoding. It has to be extensible, etc. But we don't really want to just look at the bytecode. Here's an output of a tool which gives the bytecode in more understandable format. Some parts here are important because it has like a magic, which you would expect from a container format. It has a version number. This is really important in terms of extensibility. If there would be a breaking change to the bytecode, it can be introduced through a new version number. And that way you can keep compatibility with the old code without putting much strain on the new version. Other important parts are that you have separate sections. You have sections for imports, exports, memory, functions, etc. And there's an extra section which is called custom sections, and that means you can just define your own data you want to store extra in the container. Where that comes really handy is some of you might have heard about Solidity's new feature for bytecode verification. And in Solidity, how it works is you'll, of course, have all the input sources you need to compile your Solidity bytecode. And you also have all the settings used to compile the bytecode, which might be library addresses, etc. And what Solidity does today is it creates a JSON with all the details, hashes that JSON, publishes the JSON on Swarm or IPFS, and keeps the published hash in the bytecode. So all you need to do is, on the blockchain, you need to retrieve the bytecode of your contract. You will see the hash, and using the hash, you can retrieve all the details from Swarm. So that's really interesting, but EVM doesn't really support custom sections. So it's kind of like a hack. It's data at the end of the bytecode. In WebAssembly, you can just put it into a normal custom section. So WebAssembly itself is just a specification. It's not a virtual machine. It's a specification of bytecode and containers. But there are multiple virtual machines available today, starting with all the browsers. And all the browsers, usually you would have on your computer, already has WebAssembly. You might need to enable it especially, but it would be in your browser already. There's also Node.js supporting it, a couple of other prototypes. An important part is WebAssembly as a specification is also written in OCaml, and there's an OCaml VM which would verify that the specification is correct. And here we come to the point which probably all of you are interested in. So WebAssembly itself, as explained, has all these details, and we are not here to change WebAssembly because we don't want to implement new VMs ourselves. We just want to use all the VMs and everything which is already there. So therefore, we have a limited set of options how we can extend WebAssembly. We propose what we call eWASM, Ethereum flavored WebAssembly, as a replacement for EVM. It is a restricted subset of WebAssembly. We just disable some features and define some interfaces. And from the next part of this presentation, there are going to be 3 important points I'm going to talk about. The first one is how do we achieve backwards compatibility? And the second one is how do we define metering? Because WebAssembly, as I said, we don't want to change it, and metering is not part of WebAssembly. We have to have another way to do metering. The last part is how can we interface from WebAssembly with the Ethereum blockchain? So the first part for backwards compatibility is we have a really nice tool called EVM2WASM, which takes EVM bytecode as an input, and we'll output eWASM bytecode as an output. This is a really interesting part, which might be hard to grasp at first. But essentially, we're writing this tool in C, which can be compiled to WebAssembly, and it can be deployed as a contract. And by having it deployed as a contract, you only need to write it once. Whenever you write a new Ethereum client, you don't need to write it again. And the consequence of that is that you could also meter the transcompiler. And you could charge the user, like how deployment works today is we charge based on the number of bytes you have deployed to the blockchain. But we could change that, and we could actually meter how much effort it takes to deploy a bytecode. It is, of course, compliant with official tests. It is really fast, and it is quite small. So why we have 2 parts there is we have a lot of functionality implemented in WebAssembly itself, like implementing each of the opcodes, and we have a small part which takes an input, processes the bytecode, and puts together the whole bytecode with these opcodes we have written. This is just a tool if you want to visit it. It is a JavaScript prototype where you can pass in EVM bytecode, and you will see the WebAssembly output on the right-hand side. So the second part is metering injection. As I said, we don't want to change WebAssembly itself because we don't want to write VMs. So how we can do it is we have to transform the input bytecode to a bytecode which has metering statements. So this is what you see here. First, we just take in WebAssembly as an input. We do some validations that it conforms to our requirements. And then we inject metering statements. And there you will have the output. Now, how this actually looks like is we're metering by branch. And what it means is in every program, you're going to have different branches of code. And you can jump from different branches to new branches, etc. EVM has branches itself. And you could implement this approach of metering in EVM as well if you wanted, but it's done differently in EVM today. So what you see here is we have a function which has an if statement, and the if statement has 2 branches. So what we can know from this is the if statement and the condition for the if statement has to be executed in every case. So we take this as a branch, and this is the green part. And you have the blue part, which is a different branch. And the purple part, the pink part, is the 3rd branch. So we have these 3 branches. We calculate the gas for each of these different branches. And we insert the metering statements before all of those. So here you see there's a metering statement for the if and the condition. There's a metering statement for the return, and there's another metering statement here. What this brings us actually is, in the future you might have compilers which will optimize to have longer branches, because it will be cheaper to execute longer branches, because you're going to have a single metering statement for any given branch. Okay, so we have metering there somehow, but we need to come up with gas costs for the instructions, because we cannot just carry over what EVM has, because we have different instructions. So we have created a new gas cost table based on the actual instructions. And how it works is WebAssembly was really designed to be compiled to today's computers. So it kind of maps how into instruction set looks like. And we have looked at random, well, not quite random, but the usual average computer we think would be used by miners. And that's the basis for the gas calculation today. And we have looked at the internal manuals, what kind of cycle counts each of those instructions have, and we have taken those as the gas value. However, we do realize that this is not really flexible in this way. There has to be a way to update this. We might be really wrong. Computers probably will change, and someone will come up with a much better way to define these gas costs. So we're not really building, hard coding the gas cost into any of our tools. Rather, we're going to have a contract which has the gas cost for each instructions as data. So what this means is, if there's a new change in the network whereby you have to update the gas cost, as you have seen in the past with hard forks, you could do it in a much more simple fashion. Because today you need to update each of the clients to take into account the new gas cost. In this approach, you just need to update the contract. So one way to update the contract is, of course, through a hard fork. You just update the contract itself. But if in the future somehow going to come up with a good governance model, you might be able to update it on the fly. Here's just a comparison of what we have based on the gas cost. So with the SHA-256, which is a hashing method, 8 kilobytes of input data will cost 3,000 gas with the precompile. With our gas cost implemented, SHA-256 implemented in C and compiled to WebAssembly would result roughly in 6,000 gas. So what this means is the WebAssembly implementation would be half as efficient as a native implementation. This might be wrong, but at least there's a starting point. And if you compare it, how it compares to EVM, it would roughly cost today 32 million gas, which is way over the limits you can do. And in case we would implement shifts in EVM, which would be really nice, that could go down to a reasonable level. So the third part is, how do we interface WebAssembly with Ethereum? And here we have defined a couple of interfaces in order to do that. The first interface is just a set of methods a client has to expose through WebAssembly to the contracts. And these kind of map all the calls and all the special instructions we have in EVM today. There's just a method to get the call data size, there's a method to get the call data itself, methods for storage, etc. So here's just an example based on the assembly representation I showed you before. That's how S-load would work in WebAssembly. You call the storage load itself, which takes 2 parameters. A memory offset, that's really annoying. A memory offset for the key, and we know the key for storage load is 256 bits, and we know that the result is 256 bits. So here we can just give 2 memory pointers, which are 32 bytes each. This is the input, the key itself, and this will be populated with the output once the call has finished. So it's quite simple to use. There's a second interface, which is more like a specification, what a WebAssembly contract has to look like. So it has to be in the WebAssembly binary encoding and a specific version of the decoding. It has to have a single entry point, and it can only import the methods we have defined previously. So only these methods, nothing else. We also set some other limitations, such as it cannot use floating point, etc. So here's an actual example contract, still in the same assembly representation. Here we just define a memory segment with the data. We have the return statement from Ethereum, and we just call the return statement with the memory pointers. What this contract will do is, it will return every time you call it, it will return hello world. And like the third part to all the interfaces is system contract, which all of them are written in WebAssembly, or rather written in C and compiled to WebAssembly. And these are a set of contracts we provide to all the client developers. The first one has the name of the Sentinel, and what it does, it's more like a gatekeeper. Whenever you want to deploy a contract, you feed this contract with the input. It will do the verifications, it will inject metering, and will return you bytecode which can be directly written into the state. As mentioned before, the second such system contract is the transcompiler. And of course, we have to provide all the precompiles, which we have today. So what the system contracts means here is if you are a developer creating a new Ethereum client, you have to do the networking. You have to take a WebAssembly VM from somewhere. And then you have to implement the contract interface, which is really thin layer. And on top of that, you can just take all the other parts from us, which were already pre-written. And compare that to what you have to do today, is you have to implement EVM in your language of choosing, with all the special opcodes. You have to implement all the precompiles, and the rest of the things like the networking, etc. So as you can see, that's quite a big difference. There's quite less stuff to be implemented if you use WebAssembly. So these are the 3 rules you have to follow in order to be WebAssembly compatible. Whenever you, because we want to keep backwards compatibility with EVM entirely, that means in your blockchain, you're going to have EVM bytecode already deployed, right? But you also want to have the ability to deploy WebAssembly bytecode, and they can coexist. So a new client then has to first check whether it's a WebAssembly or an EVM contract. And it's really easy to check that because we have a magic number for WebAssembly. If you do happen to have an EVM implementation as well, you can just go ahead and run EVM contracts as they are. But if you don't want to implement EVM because you are WebAssembly only, you can just use the transcompiler to prepare code for you. And lastly, as I mentioned, you have to use the Sentinel to verify and meter your contract before it's deployed. So these are the 2 implementations we have of eWASM. And they are 2 prototypes. The first prototype is called eWASM kernel. It's written in JavaScript. And that means it runs in any of the browsers, like the browsers mentioned, which have WASM support. And they also run in Node.js. It is roughly 1,000 lines of code. So that's just to show what's the amount of detail you have to implement, which is not much compared to, well, I actually don't know how big the client implementations are in terms of lines of code, but they do feel quite big. The second implementation we have for WebAssembly is called here. So this is written in C++ and uses the EVMC interface. Nobody has really heard about EVMC, but EVMC just defines a plugin system for Ethereum clients, whereby you can replace the virtual machine implementation with other implementations written in C. So what this means in our case is we can use CPP Ethereum, which is a C++ client, and we can give this plugin to it. As you see there, ETH-VM here. That's the only thing you have to do with the C++ client, and you can use it to run WebAssembly. The EVMC layer is also implemented by Ethereum, and probably it will be implemented by other clients in the future. So far I only shown you those as expressions and bytecodes. So you can actually write contracts that way, but we don't really expect people to do that. The first thing we are doing right now is writing contracts in C, which might sound crazy, but it does work. So what we do here is we use Clang from LLVM, and we have our special libc to expose all the other features we need. So that's an actual example of a precompile, and that's a SHA-256 precompile written in C. As you can see on this line here, we are just using a library already written in C for hashing, which is the embed TLS library. We don't need to change anything in that library to compile it as a contract. We can just take it as it is. The only thing we're doing here is wrapping it into Ethereum calls. So this is the actual contract I've used in devising those gas figures in the earlier slide. This was compiled to WebAssembly and executed in Hira. But I do understand that people might not be that crazy to write contracts in C, and they might want to just stick with Solidity or whatever other language they want to use. The good news is that we do have a target for Solidity, a backend and target for Solidity. That means this Solidity code here can be compiled to WebAssembly directly by the Solidity compiler. And this is the output from the compiler itself. Now this is only an experiment currently, but the good news is that Solidity is on the path to introduce an intermediate language. Because right now what Solidity does, it takes the Solidity source code, does a lot of transformations internally. At the end of the transformations, it writes direct EVM bytecode. How this is going to change is there's going to be an extra step before, which is an intermediate language, which is going to be an intermediate assembly language which supports for loops, functions, a lot of other syntactic sugar as well. And that's how most of the Solidity code will be transformed into. And that's the very last step. That intermediate representation is compiled to bytecode. Now this is where WebAssembly comes in, because we can compile that intermediate representation to WebAssembly itself. So what I really hope for is, in the coming months, we're going to have full support for Solidity to output WebAssembly from itself. So that should mean, assuming everything else we do comes along nicely, that you should be able to use WebAssembly without any disruption, without even noticing that you're using WebAssembly. Just keep using Solidity, and you get more power out of it. If you're interested in more details, please talk to us, because I know it might probably have sounded really rough, because there's just so much to cover here. We'll be around the conference, and just talk to us if you need more info. Thank you.